Hello, welcome to my video on the spherical coordinate system. The spherical coordinate system, it's a 3D coordinate system featuring our old friends X, Y, and Z. And, well, it's very useful for a variety of applications, but this isn't exactly applied mathematics so much as it is just an explanation. So let me just stop talking and get started here. Well, this is our X, this is our Y, and this is our Z axis. The spherical coordinate system, well, it goes like this. There's a big sphere that just spans across these axes. Looks kind of like that. So if we take this logic, right, and we expand upon it, I'm going to draw that same axis, our three-dimensional axes. If I draw a line segment here, starting at the origin, that spans outward, call it line segment O, because it starts at the origin, Rho. So we have our line segment here. And now I'm looking at the angle between our line segment, O, Rho, and the positive z-axis. Well, that's this angle right here. Call it angle psi. Alright, so imagine that I have a flashlight and I shine that flashlight down onto the line segment. I shine it down onto the line segment, and the line segment, well, it casts a shadow into the XY plane that's down here, the XY plane. That's going to be the projection of the line segment O, Rho. And so that's going to look like this in the XY plane. It's like a shadow. Now there's an angle in the XY plane from the projection of our line segment into the XY plane. Um, and it's the projection, it's the distance between, well, it's the angle between the projection and the positive x-axis. So that's that angle right here. And this is called angle theta. And well, I can make a couple of assertions about this image that we've drawn. That is, rho is the distance from the origin at point rho. This point right here, rho, can be written as follows. Rho is the equation, the square root of x squared plus y squared plus z squared. And this checks out because this equation here, well, this is the equation for a sphere, which we see here. So another way to think about this is that this is all within a sphere. Maybe I can dot it. That's not very good, but it'll have to do for now. See, we could even look at this on Desmos. If we look at this equation here, rho equals the square root of x squared plus y squared plus z squared. And if we put that into our graphing calculator, in this case Desmos, we can rotate it to see that this is in fact a sphere. And we know that it's a sphere because the inside is completely hollow. Now, another assertion that I can make about this is as follows. That is psi shown in blue here. Well, that's the angle between the line segment O and Rho and the positive z-axis. I got one more statement here. All right, so for theta, it's the angle in the xy plane from the projection of line segment O and Rho into the xy plane and positive x-axis, as seen in green here. So let me see here. I'm just going to move some stuff around just a bit. Let's talk transformations here. We've established that rho is set to the equation of a sphere. When it comes to the transformations of x, y, and z, if you're going from rectangular coordinate system from the Cartesian 3D coordinate system to the spherical coordinate system, x, y, and z, well, they're going to transform. And x specifically is going to be equal to rho times sine of psi times cosine of theta. Y is going to equal rho times sine of psi times sine of theta. Z is going to equal rho times cosine of psi. And these are going to be our transformations. So I could write out a formula for this, right? Imagine I have the triple integral with volume D, and I'm trying to represent the space inside for the function f of x, y, and z. It's in the Cartesian coordinate system. It's in the rectangular coordinate system. It's a function of x, y, and z. Okay, but I want to put it into spherical coordinates. Then that's going to equate out to be as follows. That is the triple integral of a function that is made up of rho, theta, and psi respectively, times rho raised to the second power times sine of psi, integration with respect to rho, psi, and theta. dv is another way to write integration with respect to x, integration with respect to y, and integration with respect to z. dv, it's the same thing as dx, dy, dv. Maybe you're familiar with the cylindrical coordinate system. Well, in the cylindrical coordinate system, we had dx and dy became rd theta. Well, now it's like for the spherical coordinate system, dx, dy, and dz respectively becomes rho squared times sine of psi, integration with respect to rho, psi, and theta. All right, so let's take our new knowledge and let's try to apply it to an example. This says to find the volume of a solid bounded by the sphere x squared plus y squared plus z squared equaling 16, and below by the sphere x squared plus y squared plus z squared equaling 4, where x, y, and z are non-negative. If we look at these equations, x squared plus y squared plus z squared equaling 16 and x squared plus y squared plus z squared equaling 4, and we graph it, we're going to get a sphere. The gray sphere represents x squared plus y squared plus z squared equaling 16, and it's going to have a radius of 4, because 4 times 4 is 16. And well, that's shown here along the z-axis. We have the radius is 4. It's coming out to about 4 here. Right, so this is our sphere. But if we zoom in, there's a second sphere inside of here. X squared plus y squared plus z squared equaling 4. That's going to have a radius of 2, right? And this is true across all axes. Radius of 2, radius of 4. So the idea here is that we want to find the region that's bounded between radius 2 and radius 4. So radius 2 being the inner sphere, and then radius 4 being the outer sphere. But if we go back to our question, it says where x, y, and z are non-negative, so they can't be negative. So that means that it's going to be in the first octant. And an octant, well, there's 8 octants. Well, we can let blue represent the top. There's going to be 1 octant here, 2 octant, 3 octant, 4 octant. All right. Then we're going to have on the lower side of this, that's going to be the 5th octant, the 6th octant, the 7th octant, and the 8th octant. So I don't know if this is the best drawing here. I know that it's not. But well, if we have like a cube, this isn't a cube, but if you were to divvy this up into 4, like if this is the bird's eye view and you were to divvy this up into 4, 1, 2, 3, 4, but then there's gonna be like a bottom side. So like this is the cross section right here. But you're gonna divvy it up. 1, 2, 3, 4, and across this way. There's gonna be 8 cubes total. 1, 2, 3, 4, 5, 6, 7, 8. If we look at Desmos, let me zoom out here for a bit. So if we look at Desmos, this might have been easier. The first octant is going to be right here, and that's going to be the positive this is going to be positive octant. This is everything here is positive in this first octant. This would be the second octant. This would be the third octant. This would be the fourth octant, and then down below, we're going to have the fifth octant, the sixth octant, the seventh octant, and the eighth octant. Now, we're dealing with a situation where x, y, and z are all non-negative, so they're all positive. That means that we're going to be dealing with this first octant right here. So we're going to disregard everything else, but we're only going to look in the first octant. So let me try to draw out what that looks like. So I'm going to try to attempt to draw out the first sphere, that is the sphere with radius 2 in the first octant. This is 2, radius 2. And now I'm going to attempt to draw the sphere with radius 4 in only the first octant. And that would be the second sphere with radius 4 in the first octant. This is at 4. This is 2. We know that the spheres of radius 2 and 4 bound the region we're trying to find. Call it region D. Okay, so 2 is less than or equal to rho, which is less than or equal to 4. So if you think about rho, right, and we can look back at our notes, this red line here, if you think about rho, that is what is the radius of a sphere that would work for the region that we're trying to find. It doesn't care about the angle, it just cares about how far that you're going to walk out from the origin is. So if you look at this, to be in the region of the volume, it has to be bigger than a radius of 2 and smaller than a radius of 4. That's how it lies outside of the red and inside of the white. It's the region that lies between the two spheres. So rho here, in this context, it's a circle between radius 2 and a radius of 4. That's all this is saying here. As for psi, well, psi is a little bit more difficult. I'm just going to try to draw this. So we have rho. Rho is, well, we're going to write that in pink now. So we got rho, it's coming out here. Now we're looking at psi. Psi is the angle between the z-axis and all of the angles that you can have inside of it. It is all of the angles from 0 degrees to 90 degrees from z to y. From z to y. Maybe we should do a different color here. All of the angles from z to y. That is psi. And I'll write it on a green line here to follow suit. 0 is less than or equal to psi, which is less than or equal to pi over 2, or 90 degrees. This is just in radians, pi over 2 radians. Now we can try to think about this in the xy plane. In the xy plane, well, z is just equal to 0. Z is equal to 0 in the xy plane, so we can figure out, like, what's theta? You know, we have to figure out what theta has to be because we are looking at the shadow that rho is casting down into the xy plane. We want to know what theta is. So in the xy plane, and remember in the xy plane, z is equal to 0, we have our equation that is x squared plus y squared plus z squared equals 16. You know, and we're just so curious, like, what's going on in the xy plane? We have the sector of our circle in the positive xy plane. We take our equation and we're like, well, z is going to get set to 0 because we're in the xy plane. So let's see what happens. X squared plus y squared plus 0 raised to the second power equals 16. Well, that's the same thing as x squared plus y squared equals 16. And this is the same thing as x squared plus y squared. That equals the radius squared. The radius squared, that equals 16. So then if we took the square root of 16, that's going to equal 4. And that means that the intersection points here on the xy plane, it's going to be 4 and 4 for both x and y respectively. You know, that's great, but like, what does that mean for theta? You know, theta, we're dealing with radians. If we think about our unit circle, right, we have our circle, we have our axes, and it starts at 0, and then it moves up to 90 degrees, also known as pi over 2 radians. And then it moves over in the counterclockwise direction to 180 degrees, which is also known as pi. And then it continues in the counterclockwise direction to where it's going to be 3 pi over 2. And then, well, 2 pi radians is a full revolution. But we're only interested in this area here. We're just looking at this area here. So if we're going from 0 in the counterclockwise direction towards pi over 2, what this means is that 0 is going to be less than or equal to theta, and theta is going to be less than or equal to pi over 2. Now I can figure this thing out in spherical coordinates because I'm trying to calculate a volume, and that volume here, well, it's going to have a 1 on the inside. It's a triple integral, where we're trying to calculate the volume D, and we're going to have a 1 on the inside, integration with respect to the volume. I'm trying to calculate the volume of this solid, and I'm using a triple integral. So I have a 1 inside the integrand since I'm calculating the volume of a solid. And this dv can also be written as dx, dy, dz. I'm just doing it in that order because it's alphabetical. I just realized something. I didn't underline this. Orange for theta. When I'm using spherical coordinates, these variables which we're integrating with respect to, namely x, y, and z, well, these things are going to get replaced by rho squared times sine of psi, integration with respect to rho, psi, and theta. Um, the 1 is still going to be in there, but the dz, dy, dx gets replaced by rho squared times sine of psi, integration with respect to rho, psi, and theta. The first of three integrals, let's do theta. That's going to be, well, it's bounded between 0 and pi over 2. All right, check. The second integral, let's do psi. Well, psi is bounded between 0 and pi over 2. And as for the third integral, that's going to be rho. And rho is bounded between 2 and 4. So just write that in. The definite integral from 2 to 4. What we're going to write in our integrand, well, there's a 1 in there. So we could put a 1 in there. Dx, dy, dz, that's going to turn into rho squared times sine of psi, integration with respect to rho, psi, and theta. And that would be the setup for our integral. So I'm going to take this triple integral and I'm going to solve it. Well, I'm going to try to solve it. So just clean this up a bit because there's a 1 here in the integrand, and let's be honest, we don't really need that. Just to reiterate, this here used to be dz, dy, dx. All right, and there's still a 1 in here to calculate the volume. So let's go ahead and solve this integral. Let's play. And we're going to work through the triple integral from the inside out. So that means that we are going to solve this first integral here. Now, right off the bat, this is integration with respect to rho. And we have rho squared, but we also have it multiplied to sine of psi. Well, psi is not rho, so we're just going to treat it as a constant. In other words, we're going to factor it out. Sine of psi, factor it out, and now we're just going to go ahead and with the integration process, integration with respect to rho. This is a power rule situation. It's going to result in, well, rho raised to the third power up top, and in the denominator it's going to be 3. And we are going to evaluate this from 2 to 4. That is, rho equals 2 in the lower limit of integration, and rho equals 4 in the upper limit of integration, or bound of integration, if you'd like. I'm using those terms synonymously. So I'm just going to write this out here. This is going to turn into, well, it's rho raised to the third power, so over 3, and we're going to evaluate this via the fundamental theorem of calculus part 2, which basically means this is going to turn into 4 raised to the power of 3 over 3 minus the rational expression 2 raised to the power of 3 over 3, I'm pretty sure. Integration with respect to psi, integration with respect to theta. 4 times 4 is 16, times 4 is 64, and then 2 times 2 is 4, times 2 is 8. So 64 minus 8 is going to be 56, I think. And so that's going to be over 3. So we'll have 56 over 3 sine of psi times 56 over 3. Well, that's in the integrand. This is going to be integration with respect to psi and theta. And, well, you'll notice that 56 over 3 is a constant, meaning we could just factor that out of the integral entirely. Both integrals. 56 over 3 times the definite integral from 0 to pi over 2 times the definite integral of from 0 to pi over 2 for sine of psi, integration with respect to psi, and integration with respect to theta. The integral of sine of psi is going to be negative cosine because the integral of sine is negative cosine. So we're going to have the result being negative cosine of psi, and it's going to be evaluated at its respective bounds of integration. So let's write that out. So that is negative cosine of psi, evaluated at, well, the lower bound psi equals 0 and the upper bound psi equals pi over 2. Integration with respect to theta. But I'm just going to factor out that negative sign. So what's this going to leave this? What's this going to leave us with? Negative 56 over 3 times the definite integral from 0 to pi over 2, positive cosine of psi evaluated at its bounds, namely psi equals 0 and psi equals pi over 2. Integration with respect to theta. Well, all we really need to do is just plug in our bounds. It's relatively straightforward. So that's going to be negative 56 over 3 times the definite integral from 0 to pi over 2. And we're just going to apply the fundamental theorem of calculus part 2. That is cosine of pi over 2 minus cosine of 0, integration with respect to theta. Now these are special angles, and well, cosine of pi over 2, it's just going to go to 0, but cosine of 0, well, that's going to be 1. So we're going to have 0 minus 1. And if we have, okay, yeah, and then here, I'll just write that out. Negative 56 over 3 times the definite integral from 0 to pi over 2 of 0 minus 1, integration with respect to theta. That's going to be negative 56 over 3 times the definite integral from 0 to pi over 2 for negative 1, integration with respect to theta. Now, if we just factor out that negative sign, it will then this negative 56 over 3 is just going to become 56 over 3 times the indefinite integral, times the definite integral from 0 to pi over 2 of 1. Well, and then this is going to be integration with respect to theta. When you're evaluating a constant, when you're integrating, when you're anti-differentiating a constant, when you're taking the integral of a constant, you literally just throw the variable that you're integrating with respect to onto that constant. And that means that we're going to have the following: 56 over 3 times theta evaluated at theta equaling 0 and at theta equaling pi over 2. And so what that's going to end up turning into is 56 over 3 times what we get when we plug in our bounds, pi over 2 minus 0. That's going to turn into 56 over 3 times pi over 2. And that's going to be 56 pi over 6. And then we can simplify this. I think this is equal to 28 pi over 3, right? Because, yeah, 8 plus 8 is 16. So I'm pretty sure it's 28 pi over 3. And that's going to be our answer. So thank you so much for watching this video. I hope that you enjoyed it. Good luck out there, guys.